This is the second video in my series of videos on Whitehead and Russell's Principia Mathematica. In the first video, I just went through some of the history, some of the background material. I had a bit of a talk about what kind of things to expect from this series of videos and what not to expect, but I didn't really make a start on the actual content of Principia Mathematica. In this video, however, I want to make a start on the first section of Principia Mathematica, so that's the section immediately following the introduction, where we introduce the axioms and the primitive notions and the primitive propositions that we're going to use to develop our logical system. One of the first things that anybody will notice that looks through Principia Mathematica is the notation. The notation is very unusual, it's very unique to Principia Mathematica, and even if you have a good familiarity with modern symbolic logic notation, you'll probably still find the vast majority of Principia Mathematica completely incomprehensible. However, during these videos, I do intend to stick with the original notation of Principia Mathematica. I won't be trying to reformulate the ideas, the propositions and the concepts in more modern notation or more modern terminology, and there's a couple of reasons for this. The first reason is that some of the ideas that play a major role in Principia Mathematica have since fallen out of use, and so there is not really any notation in modern symbolic logic that accurately represents or symbolizes those ideas. So even if I wanted to try to reformulate things in more modern notation, I could only really get a partial translation from the language of Principia Mathematica to more modern notation. So for what it's worth, I'm not going to bother doing that. But second of all, I believe that the notation used in Principia Mathematica is as accurate a representation of the ideas and the meanings that Whitehead and Russell originally wanted to convey through their work. So I think that just like any historical work, really, it's best as much as possible to understand it, to be read in its original language, because as soon as you start to translate to a different language, you're potentially going to lose some of the nuance, you're going to lose some of the meaning, and you might actually introduce some meaning that wasn't there originally, and it's going to be read in a completely different way. So for that reason, I think that Principia Mathematica is best understood in its original form, if you're really wanting to get a feel for the ideas that Whitehead and Russell were trying to get across. So in this video, I will be introducing some of the notation, just going through how some of that works, and some of the basic ideas and the basic concepts as well. I won't be going through all of the notation that we're going to need throughout the series of videos. I'm just going to go through the notation and the basic ideas that we're going to need to get us through the first few sections of Principia Mathematica, and then other notation, other definitions, other ideas are going to be introduced throughout the other videos as they become relevant, really. Anybody that's already got some basic familiarity, at least, with formal systems and symbolic logic will probably already appreciate the need for primitive propositions, axioms, primitive ideas in order to get the system actually doing something. Now, the primitive propositions are effectively our basic material from which the rest of our theory is going to develop. So the primitive propositions are accepted as self-evident, without need of proof, and from those we can then derive all the rest of the propositions in our system. We've also got the primitive ideas, the primitive concepts, which are the simplest kind of thing in our system, and as you go deeper into the system, the more complicated concepts will be defined in terms of simpler concepts, but we've got to stop that process somewhere. We've got to get back somewhere to the simplest kind of concept, and that's our basic primitive ideas, primitive notions. There's a few considerations that we need to make though when it comes to choosing our primitive propositions, because after all, there isn't a single objective collection of primitive propositions that we should feel compelled to take. It really depends what we're wanting to do. So, one of the things that we've got to bear in mind is, what do we want our primitive propositions to do? Well, ultimately, what we want them to do here is to generate as much of classical mathematics, as much as is possible of classical mathematics, from purely recognizably logical principles. So in other words, our axiomatic base, our primitive propositions, must be indubitably logical in nature. That's our start point. And we want those primitive propositions and those primitive ideas to generate a system that behaves like classical mathematics as much as is possible. So let's say we choose a particular axiomatic base, a set of primitive propositions, and from these we logically deduce that 2 + 2 = 5. Well, it's not that these primitive propositions are wrong that we've chosen, it's just that they're not doing what we expect them to do. Classical mathematics would obviously say that 2 + 2 = 4. 2 + 2 = 5 would seem a bit of a radical change. The system is not behaving like we want it to behave. It might be right for that to happen in a different context, but it's not right for it to happen in this context here. It might be that our system, as we develop it further and further, it might seem to conflict in minor ways with classical mathematics here and there, with some theorems that are kind of on the fringe of classical mathematics, in which case we might make a bit of a sacrifice there, but definitely something like 2 + 2 = 4, we're definitely not willing to sacrifice that one. So that's one of the guiding principles, one of the things that we've got to bear in mind when choosing our primitive propositions. Also, we would like our system to be free from redundancy, or at least our primitive propositions to be free from redundancy. In other words, we don't just want to cram in as many primitive propositions as we can, because it might turn out that some of those primitive propositions can actually be derived from the remaining primitive propositions, in which case that primitive proposition doesn't really belong there. It needs to be reassigned as just a normal proposition and not a primitive proposition, and then it's given further in the work along with its demonstration from the primitive propositions if necessary. We can't necessarily guarantee that our system is going to be completely free from redundancy or minimal. All we can do really is to try to identify any redundancies. But ultimately what we want to do is to generate a system that resembles mathematics. We don't really want to be too obsessed at this stage with the minimality of the system. If it turns out further down the line that it's not minimal, then we can sort that out further down the line. We would also like our system to be free from contradiction. In other words, we don't really want to be able to prove a proposition and its contradiction in the same system from the same primitive propositions. If that is the case, if we identify such a situation, there's definitely something wrong with our primitive propositions, and we're going to have to go back and we're going to have to sort that out. Again, we can't necessarily guarantee that our system is going to be free from contradiction. If a contradiction is there, then hopefully it will show up eventually. But if there is no contradiction there, we can't necessarily prove that the system is free from contradiction. There's a lot of 20th century logicians that have had things to say on this. From our standpoint, again, we're not going to obsess about it too much at this stage. What we ultimately want to do is to just choose our system, develop the mathematical system, or the system that looks like mathematics from these logical principles, and if we don't come across any contradictions, then we'll just continue as if the system is consistent. Okay, so this is where I make a start now on the actual content of Principia Mathematica. So we're going to start obviously with the first section, section number 1, which immediately follows the introduction, and in which we introduce the primitive ideas and the primitive propositions that we're going to be making use of, at least for the first part of Principia Mathematica. The first primitive idea that I want to introduce is that of a variable. Now, so far as I can see in Principia Mathematica, and unless I've missed it as I've been reading, Whitehead and Russell don't specifically introduce a variable as a primitive idea. They give an explanation what is meant by variable, but they never actually use the phrase primitive idea alongside the word variable. But I'm going to take it as a primitive idea anyway. Really, it doesn't make too much difference for what we're going to be doing in these videos anyway. It's a minor point, so I'm just going to take it as a primitive idea because I can't see any other way for it to be interpreted. There are two types of variables that we're going to be ultimately concerned with. On the one hand, we've got real variables, and on the other hand, we've got apparent variables. Apparent variables are not going to be something that we're immediately interested in. I'm going to introduce those further down the line when they become a bit more relevant. For the time being, we're going to be interested in real variables. When I say real variables, I don't mean a variable that ranges over the real numbers. Because we don't have a concept of real numbers yet, we don't have a concept of integer even, or cardinal number, or ordinal number. Our variables are, that the ranges of our variables are going to be very different things, sometimes very abstract entities. What are called sometimes individuals, which is like our basic category of things. More will be said about this further down the line. But our variables could be classes, they could be functions. It depends on the context, really. So, like a variable in mathematics, let's say we've got the function f of x equals 2x plus 7. The x there is a variable. It's kind of a placeholder for something that it's just waiting to be substituted for a specific value. Assuming x ranges over some set of real numbers or something like that. So for example, f of x equals 2x plus 7, x could be replaced with 3, and we get f of 3 equals 2 times 3 plus 7. Or we could replace x with 5 and get f of 5, etc. So our variables are going to work in kind of the same way. They have a particular range, and the variable itself can be replaced with any value from that range. So the variable itself ambiguously denotes any member really in that range of values. Again, these might be very abstract entities that we're talking about here, but the variable doesn't point specifically towards that member or that one, and it doesn't point towards all of the members of this range simultaneously. It just points towards any one, but no specific one. The way that we're going to symbolize variables is with the lowercase letters x, y, z, potentially w. And just like in our function f of x equals 2x plus 7, we could replace x with constants. We can do that here as well. Now, we won't be interested in specific constants, so we won't be interested in replacing x with Socrates or Plato or something like that, or grass. But we might want to at least symbolize the idea of replacing our variable with a constant, something which is understood to be a constant in our proofs and things like that. So if we replace a variable with something that we want to be interpreted as constant, usually, but not always, we will symbolize that using the letters A, B, or C. So we're not interested in specifics. We're not interested in replacing x with specifically Socrates or specifically this or specifically that. But if we want to symbolize the idea, then we use the letters A, B, and C. The next primitive idea for me to introduce is that of an elementary proposition. So an elementary proposition is ultimately an expression that we are going to be judging as true or false further down the line, once we've got a notion of truth in place, or something equivalent to it. So an elementary proposition is a certain kind of expression that doesn't involve any variables, and it doesn't involve the words there exists or for all. because those would be different types of propositions, not elementary propositions. So something like Socrates is mortal, or water is wet, or grass is purple. These would all be examples of elementary propositions. So as a whole, they are fixed. There's nothing, if we take Socrates is mortal, these are all fixed terms. There's no variable involved. Whereas if I say something like X is mortal, there's a variable involved. So X is mortal is not an elementary proposition. Just to note that as logicians, we're not specifically interested in particular examples of propositions. We're not interested in the proposition Socrates is mortal or water is wet, whether these are true or false. Whether they're determined to be true or false depends on the field of work that deals with that kind of thing. But as logicians, we're just interested in general propositions and the general relationships between propositions. To symbolize elementary propositions, we're going to use the lowercase symbols P, Q, R, and S. Usually it's going to be these three. Very rarely will we actually use S, but if we need it, then it's there. The next thing to introduce is the idea of an elementary propositional function. So an elementary propositional function is something like X is red. X is red, or X is mortal, or X is tall. So the idea is that we've got a variable involved here. It's called a propositional function. Functions typically have variables involved. Here's our variable X, and it ranges over a specific collection of possible values. And this itself is not a proposition. This is the propositional function. So as it is here, I can't judge this. Because it's not a proposition, I can't, strictly speaking, judge it to be true or false. But once I replace X with an appropriate value from this range of possible values, then what I get is an actual proposition which can then be judged as true or false. So an elementary propositional function is a type of function whose values are elementary propositions. Now we can, in a very, not to be taken too literally kind of way, think of an elementary propositional function as being associated with a kind of list of all of the possible values. That's not to suggest that we can literally list all of the values of the propositional function, but this is just kind of an illustration. And the X is red, for instance, we might end up with something like Socrates is red, or grass is red, and da-da-da-da-da. The elementary propositional function X is red is ambiguously denoting one of those possible propositions. Not a specific one, again, in the same way that a variable doesn't point to a specific argument, this, that, or the other, and it doesn't point to all of them simultaneously. The elementary propositional function doesn't point towards a specific value. It points to an ambiguous value, any value, but no specific one. The way that we're going to write propositional functions is typically going to be something along the lines of phi x, or maybe psi x, or psi y, and it really depends on the variable that we're using. And phi x therefore will represent, will ambiguously symbolize one of its values in the way that I've just described. So it's talking about any one of these possibilities. Now, there is a distinct. If we want to actually talk about the function phi, this doesn't do that job. Remember, this is talking about an ambiguous value of the function. If I want to talk about the function itself, I will write something more along the lines of phi x hat. The variable, the x here, really serves no purpose in many ways, in the sense that it wouldn't make any difference whether I wrote phi x hat or phi y hat or phi z hat. These would all mean exactly the same thing. So if I was talking about two different functions, for instance, phi x hat and psi x hat. I shouldn't take this as meaning that phi and psi take the same, are using the same variable, take the same variable. They might not. These variables they're not really variables as such, but they don't really have anything to do with each other. I could replace the x here with z, and I'm talking about exactly the same thing now as I was before. Phi x hat, psi z hat doesn't make any difference whatsoever. There are some variations on this notation that we're going to have to get used to as we go through, but for the time being we're going to make do with just this and this, although this is going to be the main one that we're going to be using for the time being. Just a little note as well, elementary propositional functions presuppose their arguments. So it's not that we introduce a function and then we discover the values of that function. Although that might be practically how we go about things, theoretically what will happen is that we determine all of the values of the function, all of the things that we want to be values of the function, and that determines the specific function. And there's a very good reason why we need things to work in that way, because we cannot talk about the function until all its values have been settled upon, really. So that means that we can't make the function one of its own values, because the function doesn't exist until all its values are determined. So there's nothing, we can't put the function there before it's actually being determined. And this is a very important thing when it comes to Principia Mathematica, in order to avoid the vicious circle principle. And this is tied in with the theory of types. So we've always got to be aware that a function presupposes its values and not the other way around. Now we come to the notion of assertion, and there's two types of assertion that we're going to need to consider: assertions applied to elementary propositions and assertions applied to elementary propositional functions. Assertion is effectively our notion of truth within our system. We don't define truth in our system. Assertion kind of plays that role. So effectively, if I assert a proposition, that's taken to mean in a way that I'm saying that proposition is true. If a proposition is actually false, I cannot assert that proposition. The way that, in both ways, whether applied to elementary propositions or propositional functions, I'm going to use the same symbol, which is this. So this is my assertion symbol. And if I want to say that a particular elementary proposition P, if I want to assert it, then I just write this. And this is effectively me saying P is true. So it's assertion symbol dot P. Okay. Sometimes though, I might just want to consider a string of symbols and not necessarily assert that string of symbols, so I don't want to make any judgment about whether it's true or false. And I can do that if I need to. That we will have need to do that from time to time. So we might come across something like, I'm going to have to use some notation that I've not introduced yet, but I might have something like this, which says that P or Q implies Q. Now, irrespective of whether this is true or false, I'm not bothered. Maybe I just want to consider this collection of symbols and see what results from it, and do some investigations into it. But until I know that this is true, I cannot assert it. And that's ultimately what we're going to be trying to achieve as we go through the demonstrations to the propositions, are showing that ultimately that particular proposition that we show, that we prove, can be asserted. It is true, it can be asserted. Okay, so this may or may not be true. We've also got assertion as applied to propositional functions. So we'll write something like assertion symbol dot phi x. This has a slightly different meaning, because if you remember, phi of x is not itself an elementary proposition. It's an ambiguous value. It's an ambiguous proposition, an ambiguous value of the propositional function. What I'm saying here is something slightly different to what I'm saying here. Here I'm talking about a specific proposition, which is easy enough. It's either true or it's false. Here, I'm effectively saying that whatever proposition, whatever I replace x with, whichever constant I replace x with, the proposition will be, the results will be true. So I'm saying that any value of this propositional function, however chosen, will be true. This is different to me saying that this propositional function is true for all values of x. That's a completely different thing that we're going to have to deal with further down the line. Here I'm just saying that the propositional function is true for any value, however chosen. So a slightly different thing. So there's two different types of assertion that we need to bear in mind as we go through. Now we come on to some of the logical constants that we introduce as primitive ideas. The first one that we introduce is this symbol, which represents not. So this is the contradictory function. So if I've got a proposition P, then I can negate this proposition by sticking this symbol in front of it, and this is read not P. So not P will be true whenever P is false. So that's a fairly common symbol. Anybody who's got any familiarity at all with symbolic logic will certainly have come across contradictory function. And then we've got the disjunction. Again, it's something that you'll be familiar with if you've done any symbolic logic. P or Q. This is read P or Q. So these are two elementary propositions. We're only applying these to elementary propositions for the time being, not elementary propositional functions, because there are slightly different considerations there. But not P or Q. So this will be true whenever at least one of P or Q is true. So if we've got P true, Q false, Q true, P false, or P and Q both true, then this will be true. If both P and Q are false, then P or Q will be false as well. So it's fairly typical, completely in line with modern symbolic logic and the interpretations of these symbols. There are other logical constants that we're going to be gradually introducing, in particular the implication function and logical products. We're going to have equivalence as well. We could have taken any two of these symbols. So we've got 5 symbols there: negation, disjunction, logical product, implication and equivalence. At least from the first 4, we could have taken any 2 as primitive ideas. But Whitehead and Russell have chosen negation and disjunction, and the reasons that they give for that is that it results in fewer primitive propositions required from the outset. Now, I've not actually checked this myself, but again, just going back to one of our guiding principles, really, that we really demand that our primitive propositions are minimal in many respects. Not just in terms of redundancy necessarily, but minimal. We can minimize by taking different combinations of primitive ideas. So it turns out that taking negation and disjunction minimizes the number of propositions that we need. So now we come on to our first definition. We've got the primitive ideas out of the way, we've still got the primitive propositions to go, but now we're going to start to form some other ideas that are derived from those primitive ideas. The first thing that we're going to go for, that we're going to define, is implication. So the expression P implies Q, for instance. Just a little word on definitions. Definitions are something that are not, strictly speaking, necessary theoretically within our system. They are something that go on outside the system, a kind of agreement, convenient agreement that allows us to replace certain complicated strings of symbols that occur within the system with simpler symbols. So these simpler symbols don't initially have any meaning within the system, but by virtue of their definition in terms of these already understood symbols within the system, then they can be assimilated into the system itself and become part of the system in a way. But theoretically they are superfluous. One of their main purposes is to just keep things under control. The size of the expressions that we would end up with without definitions, they would be huge. They would be completely overwhelming. With us being humans and subject to certain limitations, we wouldn't be able to interpret certain expressions beyond a certain size. So definitions allow us to condense things down a little bit. But also, definitions can actually highlight important features of the system. So if we've got a particular string of symbols that keeps frequently occurring, then it might be that string of symbols can be made into something a bit more definite through a definition, such as implication, as I'm going to define in a second. The new symbol that we introduce might give that string of symbols a completely different feel and make it feel more concrete in a certain sense. So that's another purpose for definitions. But again, they're theoretically superfluous, but we're definitely, from a practical perspective, going to need them. So our first definition then is star 1.01 in Principia Mathematica. And we get that P implies Q is defined to be the string of symbols not P or Q. And that's our definition. So what this permits us to do then is whenever we see this string of symbols, we are permitted to replace with this. Obviously we might not have P and Q, we might have something like not R or S. Well, that's fine, it's more the form that we're looking for. In that case, we just replace with R implies S. Okay, so what I was saying before about having a different feel, I get a very different feeling when I see this string of symbols than if I see this. And this is one of the beauties of definitions, that even though they're not necessary within the system, they can make something feel very different and make it feel a bit more concrete, a bit more familiar in many respects. So it could be argued, albeit incorrectly at this stage, that we haven't defined equality. We don't know what this symbol means yet. But we've got to bear in mind a couple of things here. One, this definition is going on outside of the system. This is something that exists more in kind of the natural language, rather than in the formal language of the system, some kind of extra linguistic convenience or agreement. But not only that, it's not just this symbol that's indicating the definition here, it's the whole symbol, which is these two parts. This is the whole symbol, and then we stick the definiendum in here, and then we stick the definiens in here, and that gives us our definition. Okay, so the implication function works in, although it's notated differently to what you would expect in modern symbolic logic, it's still got basically the same meaning, that P implies Q will only be false in the case where P is true and Q is false. Okay, so we've got different combinations of truth values for P and Q. This will be true except in the case where P is true and Q is false. Just a little side note on this implication. We shouldn't infer from an implication that there is a cause and effect relationship between what is implying and what is being implied. As far as we're concerned, any true proposition will imply any other true proposition. So for example, cows are mammals implies that the Earth orbits the sun. This is a true implication, it's a valid implication, but there is no discernible cause and effect relationship between the two. So we've got to be a little bit careful, because maybe in everyday speech when we talk about something implying something else, we've got some kind of idea that there is something connecting those two things. So for example, if I punch a wall, my hand will hurt. That's an implication, and there is a cause and effect relationship there. I punch the wall, and it's for that reason that my hand hurts. Whereas we're not interested in cause and effect relations here. Again, we're just interested in general relations between propositions. And as far as we're concerned, any true proposition will imply any other true proposition, irrespective of the nature of those propositions. Now we come on to our first primitive proposition, and arguably this could be ranked as maybe the most important primitive proposition of the lot. And it's our rule of inference. Without this rule of inference, we wouldn't be able to get anywhere in our system. We wouldn't be able to pass from the assertion of such and such a proposition to the assertion of such and such other proposition. There would be nothing allowing for that transition. So the rule of inference it's style 1.1, proposition 1.1 in Principia Mathematica. And it says anything implied by a true proposition is true. Okay, so I'm going to spend a little bit of time just discussing this, the rule of inference, and and contrasting it with implication, because these two ideas very often get conflated. It might be because in everyday speech, everyday language, we don't necessarily sharply distinguish between an inference and an implication. We kind of, if anything, we use the two terms fairly interchangeably. But here there is a very strict distinction between the two. It turns out that implication is just completely insufficient for what we're trying to do, unfortunately. So apologies for people who already know the distinction between implication and inference, but I'm going to spend a little bit of time just discussing this, so just bear with me, please. So let's suppose that we've got a true implication. P implies Q. Then it might feel quite natural for us to conclude here that Q is in fact true itself. But all we've got is a true implication. And in our system, the way that implication is defined, and it's a fairly common way for implication to be defined, it might be actually that the implication is true, but the consequent Q is false. This is not easy. This is not difficult to show. For example, if I take something like fish are mammals implies grass is purple. So this is a true implication. Fish are mammals implies grass is purple, but clearly grass is not purple. All I've got to do is look outside. I can clearly see that grass is not purple. So it would be very naive of me, therefore, to conclude that grass is purple based on this implication, the truth of this implication. And the problem is that the implication itself is just not sufficiently discriminatory because of the way that it's defined for me to deduce from the truth of the implication that the consequent must be true also. What I need is true hypothesis, and the implication doesn't demand a true hypothesis. The hypothesis could be false. So if the hypothesis is false, then I can't really say anything about the consequent. The consequent could be anything. It could be true, it could be false. Whereas my rule of inference, anything implied by a true proposition is true, it's very carefully worded. Anything implied by a true proposition is true. Not just anything implied by a proposition is true. It has to be a true proposition. So in other words, this demands that not only is the implication true, but that the hypothesis is also true. And from this, then I can assert that the consequence is also going to be true as well. So if we go back to our example, fish are mammals implies grass is purple. I've got a true implication, but the hypothesis is false. The rule of inference doesn't work. It doesn't allow me to transition to the consequence of the implication, which is grass is purple. Fortunately, I really wouldn't want to do that anyway in this case. To take another example, let's say we've got something like dogs are mammals implies grass is purple. So here we've got a true hypothesis. Dogs are indeed mammals. But we've got a false implication because the hypothesis is true but the consequence is false. We're not really interested in how the truth values of these propositions are actually determined. I'm just using these for illustrative purposes really. So again, in this example, dogs are mammals implies grass is purple. I'm not able to conclude that grass is purple because the implication itself is actually false in this case. So by my rule of inference, I can only conclude, I can only assert the consequence of an implication once I know that the hypothesis of the implication and the implication itself are true. Then I can pass to asserting the consequent of the implication. Just to quote Whitehead and Russell, somewhere in Principia Mathematica, I can't remember exactly where, but they say an inference is the dropping of a true premise, it is the dissolution of an implication, and that's exactly what I'm trying to do. I'm trying to take the implication P implies Q, dissolve it in the sense that I want to remove Q, take it to one side and be able to say Q is true on its own, irrespective of, without any reference to the hypothesis. Okay, it might be felt that this proposition here can actually be reduced to a purely symbolic form, but it can't be. It might be felt that we could write something like P and P implies Q implies Q. So, okay, there's a bit of notation here that I've not actually introduced yet, but this is just the logical product of P and P implies Q. And we're saying that P and P implies Q implies Q. This is a true proposition. It's counted among the propositions proved in Principia Mathematica, somewhere in section 3. But why doesn't this capture this idea accurately? And the answer to that is because this requires both P and P implies Q to be true. This does not. This will always be true irrespective of the combination that we've got in here. This could be true and this false, but the whole thing will still be true. They both could be false, but the whole thing will still be true. So there's all different combinations of P and P implies Q that could come up. Irrespective of that, we will always get a true proposition here. So this will not allow us to distinguish. We can't guarantee through this alone that P and P implies Q will be true. We just can't guarantee that because the proposition, if we demanded that, then this proposition wouldn't be general in its nature. And what we demand is that the propositions that we put forward in a symbolic form such as this, that they are completely general. There's no restrictions, artificial restrictions placed on the components of the proposition. We demand the highest level of generality. As you work through Principia Mathematica, you might find that the use of this is kind of abbreviated in demonstrations. So again, we're not trying to find a symbolic reduction of this, but you might see something like this. P implies Q, and then assert P, therefore we can assert Q. Okay, so somehow we show that P implies Q is true, somehow we show that P is true, and then we can apply this to get this. This is not a symbolic reduction of this principle. This is merely an application of this. And what we will tend to do is, rather than writing all of this out every single time, we might have a tendency to write something like this, which strictly speaking is not a meaningful set of symbols. It's just a notational convenience. We understand that the meaning of this is to be taken as this thing here, and that this is an application of this principle here. So under no circumstances should we see these in any way, shape or form as a symbolic reduction of this principle here. So in practice, if we think about how implication and inference are relevant in practice, let's take an example of maybe a mathematical proof, and how can we interpret what we're doing when we do a mathematical proof, when we write out a mathematical proof. So I'm not trying to make any claims as to what we're actually doing, just a way that it can be possibly interpreted as what we're doing. So usually when we want to prove something in mathematics, we will start with something that is true, some true premises, and we will want to show that those true premises imply something else, and then we will be able to assert that that something else is also true. Okay, so the true premises, the true hypothesis is usually accounted for. Usually we don't really go about a mathematical proof unless we know that the premises are true. We certainly wouldn't start with false premises because it'd be a waste of time. So we start with true premises. Then the proof itself that we write out can be thought of as a way really to establish that the implication is also true. So we've got the P implies Q. That is effectively the proof that we write out, in a way. That's how it can be possibly interpreted. And if we can establish that that implication holds between P and Q, because we've got true premises, we've got true implication, then we can pass to the true consequent. We can assert that the consequence is also true. So that's how we can kind of visualize imagine a mathematical proof, applying these kind of ideas to that kind of a situation. So again, I'm not saying that that is exactly what we're doing when we write out a mathematical proof, because it's not. It's just a way that it can be assimilated maybe into what we're doing here. I can think about this stuff applying. It might be sometimes that the hypothesis that we start with, the premises, are of an unknown status. So we might take something like the Riemann hypothesis, which as far as I know hasn't yet been proved one way or the other. So we might want to see what are the consequences of the Riemann hypothesis on the assumption that it is true. So we might show that on the assumption that Riemann hypothesis is true, this implies A, B or C. Okay, but in that case we are stuck with that implication. We're stuck with a conditional proposition, effectively. We can't just assert A, B and C, because it is conditional on the truth of Riemann hypothesis. So either somebody has to come along and prove Riemann hypothesis true. Once they do that, then we can pass then to the consequence of that implication and say, right, A, B and C are also true. Alternatively, somebody might come along and prove Riemann hypothesis false, in which case we can't say anything about A, B and C. They might be true, they might be false, but really we need another line of attack to determine what their truth status is. Third option might be that nobody ever proves one way or the other whether the Riemann hypothesis is true, in which case we're just stuck with the implication indefinitely. But there's nothing we can do with it until it's determined one way or the other what's going on with the Riemann hypothesis. So in practice, really we're only interested in implications where we either know that the premises are true, or at least whether the premises are of an unknown status. We definitely wouldn't be interested in an implication where we know the premises to be false, because from a false hypothesis anything could follow. And this is a confusion that a lot of people have. They think, well, surely if anything follows from a false hypothesis, why not just say something like fish are mammals implies Goldbach's conjecture is true. And the problem here is that our rule of inference doesn't apply, because we've got a false hypothesis. We're going to have a true implication, because an implication with a false hypothesis is always going to be true, irrespective of the truth or falsity of the consequence, the implication itself is always going to be true. But we know that the premises are, the hypothesis is actually false in this case. Fish are not mammals. I think that's what I said. In which case my rule of inference doesn't apply. So I can't use this as some kind of cheat of a proof to prove Goldbach's conjecture to be true. It just doesn't work like that. So I'm just going to take a little bit of a break now from introducing the primitive propositions, and I'm just going to talk about the dot notation that Whitehead and Russell use in their Principia Mathematica. The dot notation can seem a little bit fiddly to start with and maybe a little bit intimidating, but it's like anything really, you just get used to using it. The two things to bear in mind are that dots will represent either a logical product, or they will behave effectively as brackets, bracketing off certain portions of a proposition. So when I say a logical product, I mean we're going to see something like P dot Q, which we'd interpret as P and Q. Depending on the context, I might need to use a greater number of dots. And this is not a random choice, it's really depending on the context exactly what I've got involved in the particular proposition in front of me. But all of these could represent a logical product. The easy way to identify whether a dot is representing a logical product is if they're on immediately on either side of the dot there's a proposition. If a dot is behaving, or a pair of dots or three dots or whatever, is behaving as a bracket, bracketing off some part of the proposition, then what you'll see is usually that you've got a proposition on one side and then you've got a logical constant on the other side, and that indicates that you've got a bracket really, rather than a logical product. So what I'm going to do is, rather than give a set of rules about how to use the dot notation, how to interpret it, I'm actually just going to give a couple of examples. But even then, even when I've done a couple of examples, it's not going to fully explain how dot notation is used. As we go through the first few videos in this series, I'm just going to, I will explain how the dot notation is being used in specific instances, and then after a while I'll start to, I won't do that so much because I'll assume that dot notation is becoming a bit more familiar. I don't find that trying to learn dot notation through rules is going to be particularly instructive. In the introduction to Principia Mathematica, Whitehead and Russell do give some rules about use of dot notation, but they're really not that helpful in the first instance for figuring out dot notation. In the same way that learning to play chess through studying the rule book is not going to be a great deal of help. You've just got to at some point get stuck in and actually start playing chess. You've got to get stuck in and you've just got to start using the dot notation. It might mean that initially you make a few mistakes, you don't get it quite right, you misinterpret a couple of times, but eventually you start to get there, you start to make some progress. So initially dot notation for me was particularly difficult, but now I find that I can look at an expression using that uses dot notation, and I interpret it in pretty much the same way that I would interpret a modern expression in modern symbolic logic that uses brackets. It doesn't bother me too much. So I don't usually consciously think about the dots, but if I do have to, what I will usually look for is which dots are representing logical products and which are acting as brackets. So they're easy to identify, and rule of thumb is that a greater number of dots, for the dots that are representing brackets, a greater number of dots will bracket off larger parts of a proposition than a smaller number of dots. So this is one of the few times that I'm actually going to translate some propositions from Principia Mathematica into more modern notation, or at least the bracket aspects of these. Okay, so we've got here, in this first expression, we've got a logical product here, here, and here. All of the other dots represent brackets. So I don't really need to draw brackets around the P implies R and the Q implies S, but it might make it a little bit easier for me to understand if I just stick some brackets around it. They're not absolutely essential, but I'm going to put them in anyway. This dot here, which represents brackets off this part of the expression here. Got my implication symbol. Then this dot brackets off the P dot Q. Again, I don't necessarily need to include these brackets, but it might just make it a little bit easier for me to figure out what's going on. This dot brackets off the R dot S. And then these two dots here brackets off all of that. And then the three dots here brackets off the whole thing. And I've got my assertion symbol there. In this second example, I don't have any logical products. All of the dots are representing brackets. So the dot here is going to bracket off the P or R. And then I get my equivalence symbol. This dot brackets off the Q or R. These two dots here bracket off all of that part of the proposition. Equivalence symbol. I don't really need a bracket for the R here. Although this dot does bracket off the R, I just don't need to write in the bracket. This dot brackets off the P is equivalent to Q part. These two dots here bracket off all of this, and then these three dots here bracket off the whole thing. And then my assertion symbol there. And that's roughly how I would interpret, if I had to, these propositions using dot notation in bracket notation. But it's going to be very inconvenient for us to have to do this every single time, so it's definitely worthwhile getting used to just reading the dot notation directly rather than trying to translate into brackets all the time. You might have to do that at first, but try to drop that habit as soon as you can. So we're going to go back now to stating our primitive propositions, and the next primitive proposition that we've got is in many ways quite similar to the last primitive proposition in that it's a rule of inference, but whereas the previous primitive proposition was a rule of inference as applied to elementary propositions, this is going to be a rule of inference as applied to propositional functions. The reason that we need a separate rule of inference is because there are certain difficulties that arise in relation to propositional functions which we don't encounter when we're just dealing with elementary propositions. So the primitive proposition is, it's number 1.11, and in this phi x and psi x are going to be propositional functions. So when phi x can be asserted where x is a real variable, and phi x implies psi x can be asserted where x is a real variable, then psi x can be asserted where x is a real variable. Just to clarify, when we say that x is a real variable, we certainly don't mean that x ranges over some part of the real number line. X is a real variable means that x is a particular type of variable, as opposed to an apparent variable, which is something that we're going to come across further down the line. For the time being, all of our variables are going to be real variables, so we don't need to really worry too much about apparent variables at this stage. So let's look at this proposition in a little bit more detail and see why it's so important. The problems arise here because we've got variables involved. That's first and foremost why we can't apply the previous rule of inference to propositional functions, is because of the variables. The variables, each variable that appears in Principia Mathematica will have a range which is called a type. So I've not formally introduced types yet, and types won't actually really come into things until a bit further down the line. But the range of a variable is called a type, and a variable cannot jump from one type to another. It's got to remain within a certain type, and this is extremely important. It's one of the fundamental ideas behind Principia Mathematica, that we're able to control variables in such a way, because this prevents us inadvertently creating meaningless expressions and getting into these vicious circle situations that Bertrand Russell is very keen to avoid. So we've got to make sure here that all of these variables that are flying around, the x here, the x here, and the x here, are all effectively the same, ranging over the same type. Because it might happen that the variable here, x, and the variable here, x, actually are taking values from different types, and this is going to be a big problem for us if that's the case. But this resolves that problem. It ensures that the type here, the range of possible values of x here, is the same as the range of the possible values here. So that's a big weight off our shoulders if that's the case. It means that we're not going to be unpredictably jumping around from one type to another. We're going to be able to control where we are. We're going to be able to predict where we are, to a certain extent at least. That's not to say that we won't need to jump from one type to another from time to time. It's just we've got to do it in a controlled way. We can't just do it willy-nilly. So how is this problem resolved then? Okay, so let's have a look. We can assert phi x implies psi x. So I can think about this as a single propositional function, chi x if I really want to. So what does it mean to assert a propositional function? It means that whichever value I substitute for x in here, the resulting elementary proposition will be true. Now, I wouldn't be able to assert this if there were no values at all that satisfied this this implication. So there must be at least the type that x ranges over must have at least one member. We don't deal with empty types. We don't have any empty types. A type only exists if there is at least one member, let's say, in there. So there must be an A for which I can assert this implication. So now I'm not asserting a propositional function, I'm asserting an actual elementary proposition. It's a very different thing. But that means then that phi A and psi A must both be significant. And this is important because if they're both significant, and this is something that's clarified as we go on, if phi A and psi A are both significant, that means that they must take their values from the same type. They must be of the same type. So that means that phi x and psi x, the x's must represent effectively the same variable, or at least they must range over the same type. And that comes about through this here. If two functions are satisfied by the same constant a, they must both be of the same type. Remember, we can't have a variable jumping around different types. It's got to be contained within one particular type. So if x is in a particular type that contains a, and this x is in a type that contains the same a, then they must be ranging over the same type. And that's, like I say, a big weight off our shoulders. So there's quite a bit more contained in this particular primitive proposition than is immediately apparent. Even though we've not actually introduced types yet, it's not a problem. Types will be clarified as we go along, but the introduction of this primitive proposition at this stage is kind of anticipating that introduction of types in a more formal sense later, further down the line. And it's just ensuring really that the first bit of theory that we develop in the first few chapters before types are actually introduced is still going to be valid. That it's not going to need to be rethought once we do actually introduce types, that everything's still going to carry through. Because of the fact that this primitive proposition allows us to say that the type of phi and the type of psi are both the same, for that reason this primitive proposition is sometimes called the axiom of identification of type. Okay, so here's our next set of primitive propositions. These are just purely symbolic propositions. There's not really much for me to say about these. They are what they are. There's no question about whether they're true or false. They are just the propositions that are chosen to be primitive propositions. The assumption is that they are self-evident and they don't require proof. We've got to have a start point somewhere, and this is it really. So each of these primitive propositions has names. So the first one here, which is P or P implies P, is called the principle of tautology, shortened to taut. 1.3 says that Q implies P or Q. So how the dots are working here is, use this pen. So this is kind of bracketing off that part, and then this dot here is bracketing off the Q. In this one, we can imagine the brackets working like that. And the two dots here would bracket off the whole of the expression if we really wanted to do that. And that's the principle of addition. 1.4, which is the principle of permutation. We've got P or Q implies Q or P. So in other words, the order of the P and Q change in relation to this disjunction. And the dots here are bracketing off in that particular way. 1.5, which is called the principle of association, goes as follows. P or Q or R implies Q or P or R. This might at first seem a little bit unusual because comparing, if we think about what associativity means in a kind of algebraic sense, we might expect to see something more along the lines of P or Q or R implies P or Q or R. And indeed, this is a proposition amongst the propositions proved in Principia Mathematica, but it's not the form of associativity that is taken as a primitive proposition. The reason for that is, according to Bertrand Russell, which I've not verified this myself, but this form has more deductive power than this one. So whatever that means, presumably this is somehow more efficient in deriving the results, at least in the early stages. But this is something that's proved anyway at some point in Principia Mathematica. So again, how are the brackets, the dots working here? This dot, we've already got some brackets in here. Actually, we could replace these with dots, but for some reason we've got brackets involved, and this is how it's stated in the book as well. So this dot here is going to bracket off that part of the proposition. This dot will bracket off that, and then the two dots here will bracket off the whole thing. And then finally, principle of summation, number 1.6, which says that Q implies R implies P or Q implies P or R. So again, the brackets, the dots are working in this kind of way. Get something like that. And these are some more of our primitive propositions. We've just got a few more to go now. There's not really much else that I can say about that. They are what they are, and these will be used quite extensively, at least in the first parts of the first few sections. So now we come on to our final three primitive propositions. At least for the time being, there'll be more primitive propositions to be introduced further down the line. These are fairly straightforward. Number 1.7, if P is an elementary proposition, not P is also an elementary proposition. Number 1.71, if P and Q are elementary propositions, P or Q is an elementary proposition. There's nothing particularly difficult about these two propositions. I don't really have anything to say about them. Number 1.72, however, is a bit different. There's a bit more substance to this one. So if phi p and psi p are elementary propositional functions which take elementary propositions as arguments, phi p and psi p is an elementary propositional function. So the requirement here that phi and psi both take elementary propositions as arguments ensures that they are both of the same type. If they weren't of the same type, I wouldn't be able to form this function here. Now, this is actually quite a specific form of this. It's called the axiom of identification of real variables. A more general form of this is going to be introduced further down the line, because typically we won't be interested in propositional functions which take elementary propositions as arguments. We're going to be interested in propositional functions which take arguments from a range of different types. Remember, our types are our ranges of values to which we limit our variables. So what we will end up demanding really is that if we're going to form this function from these two functions, these two separate functions, we need to make sure that they're of the same type. So more generally, rather than having phi p and psi p with elementary propositions as arguments, we're going to have something like phi x and psi x. And what we need to do, if from these separate functions we want to form the function phi x or psi x, we need to be sure that the type of this function is the same as the type of this function. If they're not of the same type, I'm not going to be able to form this. Because if they're not of the same type, then there's no value that I can select that is going to make this proposition here significant. Let's say I choose a value that's valid for phi. If psi is a different type, that value, a, let's say, is not going to be significant here. Psi a is effectively going to be a meaningless expression, and therefore phi x or phi a or psi a would also be a meaningless expression. So this might make sense, but if this is a different type, then this won't make sense, and therefore this won't make sense. And vice versa, if I choose a value a for which psi is significant, but phi is of a different type, then this is going to be meaningless as well, which means that this is also going to be meaningless. So I need to ensure that phi and psi are both of the same type if I'm going to form this. And this is just a special case where rather than having a general variable that can take its values from a range of different types, we just stick to elementary propositions in the first instance, and that sees us through, at least for a while, through these first few sections of Principia Mathematica. So that brings us to the end of this video pretty much. I've introduced all of the primitive propositions that I need to for the time being, all of the primitive ideas. The video's gone on for a little bit longer than I expected to. There was a bit more that I needed to talk about than I originally anticipated. Even so, despite the length of the video, I don't doubt that there will still be some things that I've overlooked. The pages of Principia Mathematica are absolutely packed with information. There's little nuggets of information all over the place, some of which I've almost certainly overlooked. If there are still any gaps in my explanations, things that are still not quite clear, hopefully those will be resolved as we progress over the next few videos. If there are any things that you want to ask, then please feel free to get in touch with me, and hopefully I'll be able to resolve any issues that you've got. But on that note, I'm going to finish this video. In the next video, we're going to move on to sections 2 to 5 of Principia Mathematica, which are some of the basic propositions. So I'll look forward to seeing you in the next video. Thank you for watching.